If you have solved any kind of problems related to greedy algorithms, you will know that these kind of problems contain a lot of spoilers. That is, if I give you the reassurance that this problem can indeed be solved via greedy algorithms, then the solution becomes pretty trivial, because the hard part of greedy algorithms is proving that they are applicable to this problem, that a greedy strategy indeed works. But in this video, I want to show you a problem where I will tell you right from the start that the solution is a greedy strategy. But finding that greedy strategy is definitely non-trivial to come up with. And along the process, we'll also see a very cool transformation that can help us prove why this greedy strategy is actually correct. Otherwise, you can try this problem, you can try to pause this video and come up with a greedy strategy. No matter what you try, you will see that it becomes very difficult to prove why greedy works or what exactly is the greedy strategy. So let us start with the problem description. It says that you are given an array containing some integers and you are also given an integer k. So k means you have to split this array into k disjoint blocks. So you can see that I have created one block of blue color. So let me label this as the first block. This is the second block. This is the third block. This is the fourth block. And this is the fifth block. Then you are allowed to choose any distribution of the block as long as you have created exactly k is equal to 5 blocks. So, and each element has to be in exactly one block. That is for sure, because you are partitioning the array. Now, once you have done this, you consider any index. Suppose this is ai. Then you find out what is the block number that it lives inside. So suppose this element ai lives inside this green box. So if it is in this green block, then the index of this green block is 3. So you multiply it by 3. And then you find out this value for all the AIs. And then you sum them up. So that is why the sum is A of I into the block index of I. Meaning which block does this element reside in. And you have to maximize this sum. So how do you solve this problem? You can try various approaches on paper, and you will see that you will most likely run into various issues of proving why the greedy strategy is correct or what exactly is the greedy strategy. Because if you think about the first block, will it contain one element or should it contain all of the element? Or like, should it stop in between? But if it should stop in between, then where exactly to stop? Like, what is the greedy strategy? So you can notice that if you increase the size of the block, then you get more elements inside your block. So first of all, let us simplify the sum. So the sum says that for each element I, you have to compute this number and then you have to sum it up. So can I just reword it and can I say something like the answer is nothing but answer is equal to 1 into sum of elements inside the block. So let's say sum of block plus 2 into sum of block of this one, right? Sum of this block, sum of block 2, and so on. This means that given this expression, if you have a bigger block, you will get more sum. So definitely to maximize this value, you want a bigger block. But the problem is, if you take a very big block, then you have to assign the block index 1, right? So this this situation is something like this. You want to maximize a into b, but if you increase b, if you increase this a, which is basically the sum of elements in the block, then this B you won't get a lot of benefit. But if you try to increase this B, that is, if you want to try to have as many blocks as possible, then the sum of elements inside a block will not be that much, right? Because now each block contains only one element. So you can see that there is definitely a trade-off over here. So I can say that there is a trade-off, because whenever you encounter a situation where you want to maximize A into B, and increasing this comes at a cost of decreasing this, and increasing this comes at a cost of decreasing this, then there is definitely some dynamic programming involved to solve this problem. So anytime the word trade-off comes in, there are only two possibilities. Either it can be solved via dynamic programming, or you go via the brute force route and you compute all the possible block distribution. But I'm telling you that this problem can indeed be solved without using dynamic programming, and anyway brute force is not an option, because we want to solve it in O of n. We can't try all the possible start position for the first block. Okay, so how do we exactly solve it? And see, for this problem, anybody with a sane mind, they would try to apply the greedy strategy on the first block, and they would try to figure out where does the first block end, right? If I tell you that this problem can indeed be solved via greedy, but let's try to view this problem from a different perspective, and this perspective that I'm going to introduce, okay, that might sound a bit weird, and it might seem like that how come we started thinking in this direction. But these are the things that the first time you encounter, these might look very out of the blue, but the more you solve these kind of greedy problems, the more you get exposed to these ideas, and then these things do not start feeling odd. One example is the GCD. So I have seen a lot of beginners where they get pretty confused, like how come GCD starts appearing in problems that have nothing to do with GCD at all. But if you have been on Codeforces long enough, you will know that this GCD creeps up in a lot of problems, and after some point of time, you stop finding it surprising that GCD is applicable. So this is the same trick that we are going to use. So enough rambling. Now let's start with this block that we have, and we know that sum can be expressed as the sum of elements in the block into 1 plus sum of elements in the second block into 2, and so on. So what I'll do is I will assume any random distribution of the elements, right? I have not made any greedy assumptions so far, and assume that you have distributed some elements, and the sum of all of these elements you have to compute, and this sum can be anything. So let me call this sum as A. Sum of all the elements in the second block, let me call this as B. Sum of all the elements in the third block, let me call it as C. Sum of all these elements, let me call it as D. And sum of all these elements, let me call it as E. So what is the answer for this distribution? So the answer is A into 1 plus 2 into B, right? Because the block indexes are 1, 2, 3, 4, and 5. So the answer would be 1 into A plus 2 into B plus 3 into C plus 4 into D plus 5 into E. Right now we have not made any assumptions about A, B, C, D, and E. These just represent the sum of elements in the blocks that you have chosen. So this is just solving the problem for a general distribution. Right now we have not made any assumptions. Now I will do some transformation, and there is not really any intuition behind it. It's just something that you have to see. You just have to follow along. But once everything comes together, then you will realize why we are doing this transformation. So you can notice that what is something that is common in all of these. So there are five terms. There is one A over here and 2B over here, C over here, D over here, and E over here. So you can see that this has B 2 times, this has C 3 times, this has D 4 times, E 5 times. So borrow can I borrow one B from here, one C from here, one D from here, and one E from here? Yes, I can, because they have more than one, right? So can I write the answer something like this? Answer is equal to 1 into A plus I have borrowed 1 B, C, and D and E from everyone. So can I write it something like 1 into A plus B plus C plus D plus E? And after that, what would I have remaining? So I would have remaining. So B, 1B is borrowed, so it will become B. 1C is borrowed, it will become 2C. 1D is borrowed, it will become 3D. And this will become 4E. But what is this number that we have just created? A plus B plus C plus D plus E. This number is nothing but the sum of the entire array. So, okay, if that is what we think, can we just write it something like this? Answer is equal to sum of all plus this quantity. But this quantity, you can see that this resembles this. A structure that looks like 1 into something plus 2 into something plus 3 into something. So can we apply recursion and do the same thing over here? Means, can I borrow one C from here, one D from here, one E from here? So let me do that. So if I do that, you can see that I can get B plus C plus D plus E. And what is remaining after this? So you have borrowed one C. So the remaining part is C plus 2D plus 3E. But what is this number, right? Because this was sum of all arrays, that is fine. But what is this number exactly? B plus C plus D plus E. So this B plus C plus D plus E, this is nothing but the suffix sum that starts at this block. This is the starting point of the suffix sum. So this is interesting. So this means that the number that we first saw, we shouldn't have interpreted this number as the sum of all elements. This is actually the suffix sum starting from the first block. So can we write it something like this? Answer is equal to suffix sum of A, meaning suffix sum that starts at the first element of the first block, plus what is this quantity? The suffix sum that starts at the second element, which is nothing but suffix sum that starts at the beginning of block B, block representing this. Okay, that's fine. But this is an interesting pattern that is emerging. But is it actually true? Because if anytime, just because something appeared 2 times doesn't mean it will appear 3 times. But here it might. So let's see. So you have the same pattern 1, 2, and 3. So can I borrow one D and one E from here? So it will become C plus D plus E. And what will the remainder be? It will be D plus 2E. But what is this C plus D plus E? So C plus D, C means sum of this entire thing. D means sum of this entire thing. E means sum of this entire thing. So C plus D plus E is nothing but this suffix sum that starts at this block, right? So can I write it something like answer is equal to S of A plus S of B plus C plus D plus C, means suffix sum that starts at the third block. And then can I repeat the same thing? I borrow one E from here, so I would get D plus E, right? And the last quantity would be E. But what is exactly D plus E? So D plus E means sum of these entire elements and sum of these entire elements and their entire sum combined, which is nothing but the suffix sum that starts at this index. So can I write it something like, and what is E? E is the suffix sum that starts at this block. So an interesting observation emerges that the answer, so notice that we have not made any assumption about how we have distributed the blocks, but still the answer comes out to be the suffix sum that starts at the first block and the suffix sum that starts at the second block, suffix sum that starts at the third block, that starts at the fourth block, and that starts at the fifth block. Meaning, can you now see the greedy strategy? You can try to pause the video and see the think of the greedy strategy for yourself. But you can notice that if you compute the suffix sum array, if you compute the suffix sum array, note that we had not made any assumptions about the starting point of the blocks, right? This means that these are just arbitrary numbers on the suffix sum arrays. So which numbers would you pick to maximize this sum? Of course, you would pick the k largest element in the suffix sum array. And that is indeed your answer. So the greedy strategy wasn't to pick the first block greedily. This problem can indeed be solved via greedy, but the greedy strategy had to be applied on the suffix sum array. And in this suffix sum array, you pick the k largest element in the suffix sum array. But there is one catch, that this element, this entire suffix has to be included. Why? Because no matter what distribution you do, this was the sum of all elements, right? This is what we had decided. So even if it is not giving you a lot of benefit, even if it is not amongst the k highest element, you have to include this, right? Because otherwise you will not be able to take you cannot ignore the first element. But if you cannot ignore the first element and then you are creating blocks like this, then this suffix sum will definitely appear, because you can definitely borrow one B from here, one C from here, and one D from here, and one A from here to construct this entire thing as suffix sum of the 0th element. This means that the optimal strategy is to pick k minus 1 largest element from the suffix sum array and the S0, basically the first element of the suffix sum array. So this is the algorithm to solve the problem. Now, once you have solved this problem, the solution looks pretty easy, right? Like, sure, suffix sum, and you sort all the elements and then pick the k minus 1 largest element. But if I had given you this problem and I had given you this expression and I told you that the answer will involve suffix sums, you wouldn't have believed me, because how come these expression suddenly involve suffix sum? So this is the exact same thing that happens with beginners to GCD. They get utterly confused, like why did GCD suddenly show up in a problem? But I hope that you still found this video interesting, that whenever you have this pattern, it might still be difficult to see the math of all of this is fine, but you might still wonder, like, would you have been able to still figure out that this problem deals with suffix sum without actually doing the math? And if you can, it means that you really have good intuition for solving greedy problems.